So now let's take a look at what happens as the numbers get larger. So those are all numbers that we can actually see the factors of pretty easily, so we can look for a GCD. So finding the greatest common divisors for small numbers can prove to be quite easy. Finding the GCD for large integers can prove to be quite cumbersome. For example, try enumerating the list of divisors for 4,567 and 3,360. For that reason, we'd like to examine a recursive process that's called Euclidean algorithm. We will need to remember the technique for dividing one integer from another that we learned in 4th grade after completing the division of 28 by 11. So as a quick recall, so we have 11 divided by, 28 divided by 11. This is my divisor. I had to think about that for a minute. This is my dividend, and this would be my quotient up there. All right, so 11 goes into that 2 times. That would be 22 with a remainder of 6. So that would be my remainder. Remember that when you're in elementary school, you wrote R6 on there. Now we'd write that as 2 and 6/11ths. But we're going to see how to write that now in this recursive process that we're going to call that we call the Euclidean algorithm. All right. All right, so here we go. In this circumstance, we call 2 the quotient and 6 the remainder. And so, and observe that 28 will be written as, the dividend 28 will be written as below. And so in this case right here, the dividend is 28 is equal to 11 divided by 2. I think I got my vocabulary backwards on the last one. So 11 times 2, that's how many times it went in, plus 6. And so we can go ahead and call this our A value. This is our B value. This is our quotient. And that is going to be our remainder. And so we can kind of relate that to our generic formula down here at the bottom. All right. So now find the quotient remainder for the following. So still doing this process, we're going to take 14. We're going to divide it into 32. 14 goes into 32 2 times. I get 28. I get 4 left over. So now I can take that and plug it into my particular problem here to get my actual equation. So in this case right here, this guy is my quotient. This guy is my remainder. And let's see, and 32 is my A. So in this case right here, we ended up getting 32 as my A is equal to my B, which is 14. And 14 and B is known as my divisor. And we multiply that by 2, and we add 4 to it. So that's my remainder right there, remember? So my remainder. All right, this is my quotient, and so forth. All right, so that'll allow us to get this like algorithm here, or this recursive process going. So you can take a look at the second one there and kind of work that out and play around with it. So in theorem 14, it asserts that if integers a, b, q, and r are related by the equation, then the set of common divisors a and b is equal to the set of common divisors b and r. So sorry about that. It follows that the GCD of AB is equal to the GCD of BR. So the Euclidean algorithm is a recursive process that uses this observation to replace the task of finding the GCD of AB, where A and B are really large, by the task by finding the greatest common divisor of a very simple case. So let's take a look at how this looks. So we start off and we've got this idea that we're going to let the set A be equal to all the A's and the set B be equal to the B's. We're going to find a Q and an R such that the A's are equal to our B times our Q plus our remainder. All right, and so we'll replace A by B and B by R. So if R is greater than 0, then we repeat step 2. When R is equal to 0, the current value of b, the last non-zero of r, is the greatest common divisor. So let's kind of work through that and kind of see what that means. All right. So here's our example. We kind of broke it down by pieces, so it kind of help us see things. Let me move this up here out of the way. All right. So find the greatest common divisor of 36 and 14. Still inside of our wheelhouse, we're just doing it with smaller numbers to make sure we understand. So if that's the case, then that means that A is going to be our, 36 is going to be our A, and 14 is going to be our B, and we're looking for a remainder. So we go through and say, okay, well, what would we have to do? So to get the 36, we take our 14, we'd multiply by 2, and then, sorry about that, and then we'd add 8 onto that. So that's where 14 times 2 equals 8. To be able to get to 14, that's our dividend. To be able to get to that, we would take 8 times 1 and then add 6 to it, and that would give us our 14. And this right here would be 6 times 1 plus 2. That would be equal to 8. And in this case right here, this would be 2 times 3 plus our 0, and that would equal 6. So the current value of b, the last non-zero value of r, is the greatest common divisor of 36 and 14. So the greatest one where our r is equal to 0, we have no remainder. So 2 would be our greatest common factor because we have nothing left over. So all of these we have leftovers, whereas this one, 2 was divided in evenly, and so that's why we have a remainder of 0. So therefore, the greatest common factor is just 2, the greatest common divisor. All right, in example B, very similar problem. I'll kind of let you work your way through that and kind of take a look at it. But the idea is to use the observation from Theorem 14 to show the Euclidean algorithm did indeed produce the greatest common divisor. We can use the equations of the first column together with our insight from the Theorem 14 to conclude that, the GCF of 36 and 14, which is equal to 2, is equal to the GCF of 14 and 8, which is equal to 1. That's interesting. Let me hit pause real quick. All right, sorry about that. So kind of I'm trying to dig through this last statement right here and making sure that I can explain it to you thoroughly. Is that, why can we say that the GCD of 36 and 14, which is the first column, the 14 and 18 in the second column, 8, 6, and so forth, is that if we look at the equations in column 1, so that's the equation column, and we look through this, we can see that on the last one, equation 4, we can see that our greatest common divisor is 2. And then inside of each one of these, we can see a factor of 2. So if we go through and test this, and we know that our numbers are, for example, in this case here, 8 and 6, well, 6 is not going to divide into 8. So, but 2 would. Go up to the next one, 14 and 8. 8 doesn't divide into both, but 2 would. And go into the top one, 14 doesn't divide into both, but 2 would. And so we would just have to rearrange these equations. So just kind of becoming familiar to be able to say that that's why. Like we can take a 2 out of each one of those. And so that kind of gets us through that process of why does that show us the greatest common divisor is 2. All right, and so last little thing here is well, let's actually apply it to some actually big numbers. So our A value is 252, our B value is 180. So we plug that in and say, okay, well, 252 would be equal to 180 times 1 plus 7. Well, that's not correct. So where did we go wrong there? Plus 72. Sorry about that. So there's supposed to be a 2 right there. I'm going to hit pause and just put that in. Sorry about that. So 180 times 1 plus 72 equals 252. So that's our A and our B value. So we go through and we take a look at this, and what we see is that we're looking for, to find the greatest common factor, the greatest common divisor, we're looking for a remainder is equal to 0. So we found that if we took 36 times 2 and then added 0 onto that, we would get our greatest common divisor of 36. And that actually works for all of them. So 36 will go into 72, so that worked for those two. 36 will go into 180. So what we ended up doing is that we have this harder problem, but because we break it down going across the steps here, so 252, 180, 180 and 72, 72 and 36. So we're just continue to break that down. We get to a spot where we can use this third column, or third row, excuse me, to help us understand our GCD of our particular problem. All right, and that's it for this particular one on Euclidean algorithm, all of 3.4. Good luck.